content we have planned. We might do repeats of these closer to the Artemis decommission date if need arises. The sessions that we've hosted in the past are available as a live recording. So if you miss those on PBS Scripts, Walltime, data transfer and benchmarking and optimising your job, please visit the Sydney scheme page and you can watch those. This session is also being recorded, so you can go through it again later on. Also the content, which I've dropped a link for in the chat, is very comprehensive, so you can always refer back to that later. There's a lot to get through today, so we do need to go a little bit of pace. I'm not sure how long it's going to take. It's quite dense, but the key message, which hopefully will become clear as we work our way through, is while the NCI parallel method of running parallel jobs on Guardy is quite complicated at first glance, it's actually quite simple. And if you've got existing Artemis job arrays that you have been running, they're not going to be that difficult to port to NCI parallel. So if you're finding some of the content a bit difficult to comprehend, don't worry. You can look at the examples towards the end of the content where we show you an Artemis script and a Guardy parallel script side by side, so you can see how you can port your own scripts. So with that, I'll just start sharing my screen. So when we're talking about parallel jobs on Guardy for this session, we're talking about embarrassingly parallel jobs. So naturally, a parallel job is one that is large and can be broken down into numerous smaller tasks to be executed across multiple processes, nodes or cores simultaneously to speed up computation. So embarrassingly parallel jobs are a subset of this kind of job where the tasks are completely independent. There's no inter-process communication or shared memory. So the other type of parallel job where there is communication and shared memory required, we're not covering in this particular example. That's not what NCI parallel is for. Before I continue, just quick confirmation. Can everyone hear me okay and see my screen?
Yeah.
Great, thank you. So in order to run parallel jobs on Guardy, NCI have created a task farming tool called NCI Parallel, and it's paired with OpenMPI for distributing your parallel tasks across the compute resources on the Guardy queue within a single PBS job. So to do this, you'll need between 2 and 4 job files, depending on the nature of your workflow. Of course, you'll need a PBS script. This contains the directives to launch the job. Within this script, you'll assign a value to CPUs per task and also specify your inputs for each parallel task as well as a task script if required. And then you'll have the call to OpenMPI and NCI Parallel to perform the allocation of tasks to resources in parallel. You'll also need some kind of input arguments or commands file, and this is just a plain text file where each line of that file has a different command or argument to be run in parallel. So each line is a separate parallel task. And then optionally, you might have a task script, something like Python, Bash, any other language that contains all of the commands to run the job. If your job happens to be a single line command, you don't need this. You can just put that at file 2, the input script, but most jobs would typically require some kind of task script with a number of different commands. And then finally, if your inputs are quite complex, so you have a lot of metadata that you need to pass to each task, you might find it useful to have a helper script that makes that input file for you. On the NCI page, if you follow that link later, you'll see an example where they have a 1,000 task input list and a command script called test.sh. So what they've done is created the input commands file where the task script and the arguments provided to that task script are within the same file, and then the task script is separate. So that's one way to do it. Another way to go about it is to have your input arguments separate to your task script. Personally, this is my preferred way. I find this a little bit more portable because then when I'm rerunning the same analysis on different data sets, I just rerun my helper make input script, which creates my metadata inputs. My task script is completely separate. It's more clean that way. And if I wanted to update tools or parameters, I'm just editing in there. And then finally, as I said before, if you have a one-line command per task, you can simply create an input commands file. So all of these three options will achieve the same end result, just with a slightly different collection of files required to run the job. The PBS script is very similar for all three. You've got directives, setting your number of CPUs per task, load the modules, including NCI Parallel and any modules that your analysis requires. You will also specify the task script or input arguments or command files, and then you'll have an NCI command at the end. If you're calling one like the NCI example, you simply need to point to these two files. If you are going to have a separate arguments and task script, then you just combine those two together with an extra line of code in here with sed. It's very straightforward to do. So of course, before you go ahead and submit these, it's very important that you check that it's set up correctly, and we will cover that in a later section. So we'll start with a simple example. This is using a trio of job files. So option 2 here, arguments are separate to the task script. And in this example, there are 12 input arguments, and each task is going to run on one CPU, and the job is requesting 12 CPUs in total. So it's going to run all single CPU tasks at the same time, or in other words, concurrently. If this requested 6 CPUs for the job, only 6 of these tasks could run at once. So the first 6 in the list would run, and then when they completed, the next 6 in the list would run. So here we have our loading of the NCI Parallel module and any other tool modules you might need as well. Setting our user-defined variable, this can be whatever you want it to be, but if you do change this value, obviously make sure you change it further down as well. So 1 CPU per parallel task. I'm defining the task script and the inputs file. And then down here is where the configuring of NCI Parallel is done. If that looks a bit daunting, don't worry, you can simply copy paste this for your own purposes and it will run no matter what your setup is up the top here. So we'll look at these equations in a bit more detail. The value of M is going to determine the number of tasks that can run per node in the requested queue based on the chosen provision of CPUs per task. So this environment variable here on the normal queue is 48, and we have set n CPUs, i.e. number of CPUs per task, to 1, so it's simply 48. We're not going to run that many tasks, we only have 12, but that's the maximum value that can run per node. The next part of the equation is down in the MPI run command, where it's combining that value of M with PBS n CPUs. That's an environment variable, which is the number of CPUs that you have requested in total for your job in your directives. And then again, dividing that by the number of CPUs on the node that you've requested in that queue. So that equates to 12. So this is going to run 12 processes or tasks in parallel with the MPI run command. And then finally, we have map by node, and this PE stands for processing elements. And this indicates that each distributed task will be allocated on the node with our value of n CPUs, which is 1. So 1 CPU per processing element. And then at the end, we have NCI Parallel. So this is the application which is actually being run by MPI. And we've just got a verbose flag there to print out some information to the logs. And finally, our input file. So this is created on PBS Job Arrays, which is the local to the node solid state drive. This file is deleted after completion, but we don't need it. It's created by this sed command I mentioned earlier. Combine the task script with the arguments to make the command file. So this is our option 2 example where our inputs and script are separate. So NCI Parallel will take each line of that input file and allocate each line to resources based on the equations above, which say how many resources can run per node, how many to run at once, and how many CPUs to give each. So now we've had a look at that setup, a quick test of understanding. Think about how many tasks could run per normal node if we set the value of n CPUs to 6. So we know that there are 48 CPUs on the Guardian normal nodes, and we want to run 6 CPU tasks. We could run 8 tasks per node. If we wanted to run 10 normal nodes for that job, on the same 6 CPUs, of course, it is simply 10 times 80 times 8, which is 80. So we could run 80 tasks at once if we requested 480 PBS and CPUs. So now the input arguments file. For this demonstration, it's really simple. I just use the shov command to create 12 lines of numbers. If this was a more complex setup, of course, you could use a script to write your inputs file. And then finally, the task script. It's just reading in this single variable, 1 line per task, and it's going to print it out. And then you just submit it with QSub, the same as any other type of job. And unlike on Artemis with job arrays, you would see the square brackets when you ran QStat. For NCI Parallel, because it's one job with a lot of tasks happening, it just looks like another normal job. Excuse me. So you won't actually, it won't look different because it's a parallel job. When you check the completed log, you'll see your same kind of research summary that you get in a typical O log, looking at our exit status of 0. And because I didn't redirect the output in my task script, it's all getting written to the .o log file. Now, this is not recommended, it's just a demo, because you'll notice that these numbers are actually in a different order. 48 and 51 printed first, whereas 51 and 20 were first in the inputs. And that's because all of the tasks were running at once. There's no indication of which is going to start first or finish first. So that's obviously not great. If you've got a lot of I/O happening to your .o log, you can actually end up with lines running over each other, jumbled output. So always redirect your important output. You don't get separate .o log files per subtask like you do with a job array. Now looking at the .e log, you'll see a bit of information here from NCI Parallel about the node that it was run on, the job ID, and also each task has an exit status. Here we have 0, which is great. And after the exit status will be the actual line that was provided as the task by the NCI Parallel command. So if you had a lot of complex arguments, that all will be printed out here. And this is quite useful when you're trying to identify and rerun failed tasks. You can pull them out of this .e file and then create a failed inputs list to troubleshoot and resubmit later. So it's important to note that the exit status, as always, does not indicate a successful job, both within the PBS script .o and .e. You should always check your outputs. And it can be helpful to write a checker script, because if you've got thousands of parallel tasks, you don't want to check all individual outputs. So you can write some kind of logical checker and loop over all of your outputs. So this script, a quick and dirty way to check that is to pull out the number of lines with exit status 0, and that should match the number of lines in your input. One way where this is not ideal is if not all tasks start. For example, if the task failed on Walltime, you'll see that only 5 of the 12 tasks actually got a chance to start. So the remaining tasks don't even appear in the .e exit status. So in this case, instead of trying to rely on your .e log file to identify failed tasks, you would need to pull them out of your inputs file, every line that didn't have exit status 0. So now we'll move on to checking the parallel job. There's a couple of different checks you should do. First of all, check that your task script reads in the arguments correctly. And this is the same as what you would do on Artemis for a job array or any other job, just basic sanity checks. The second check is to make sure that your task actually executes on the compute node. And this can be a really handy way to identify if you've got your L storage directive set up properly. Typically, if you forget that, you'll get no such file or directory, and that can be quite puzzling until you remember, that's right, Guardi needs this directive that we didn't need on Artemis. And then finally, that the MPI run binding of tasks to resources is set up correctly for your job. So checking the task scripts, reading in the arguments, you might have a test condition in your code. If so, please go ahead and use that. If not, a simple way to do it is to just add some kind of checking print statement into your task script and then run that on the login node, not the compute node, providing one line of your input arguments file, the same as what would be run when the task was executed on the compute nodes. So we put an exit in there, so none of the actual tasks is run on the login node. So in this example, I've just taken the first line of the demo.inputs file and then run my demo.sh script as a simple bash script, providing that first line of inputs. And then I've got some sanity checks I can check that all my variables look good, nothing's empty, and that all my input files were readable and not empty. So once that check has been passed, you can go on to checking the task on the compute node. So ideally, you've already done some benchmarking. If you're not familiar with that, please follow this link to our session on that and potentially watch the recording. You should be having a good understanding of how much resources each task needs by the time you get to this point. So this is a place where you're just going to run one single task on your chosen resources and test that, first of all, the arguments are doing what they are meaning to do, or your output is going to the right place, your else storage is correct. And this will also help you test that your MPI run command is correct, because if there's something wrong there, then it will meet a fatal error. So a simple way to do this is to create a single line test input, same as I did before, using a head command to get one line, but saving it to a test inputs file, which is one single line, and then adjusting the resources for the job. So I'm not going to run 5,760 CPUs for the whole parallel job. I just want to run one task, which I've benchmarked needs 6 CPUs. So once that's done, of course, we need to change the name of our inputs file. We're going to run on a single line test input file, and everything else can stay the same. And then simply submit that on the to the scheduler. So if it's a long-running task, you might choose to let it run all the way through to check that everything is working perfectly before you set up run your full job. Or you might choose to let it run for a few minutes, sufficient to identify that everything's working okay, kill it, and then resubmit the full job. And now finally, we're going to look at checking the binding of resources to parallel tasks. So this refers to how the tasks are actually distributed to the resources by OpenMPI. And we'll look at 2 different ways of doing that. On the NCI example, you'll see they've used the MPI run map by parameter in a slightly different way to our simple example we looked at earlier, which had map by node. So what's the difference there? PPR stands for processes per resource, and that specifies the number of tasks that is assigned to that resource. And resource could be NUMA, socket, or node. So a NUMA node or NUMA domain stands for non-uniform memory access, and it's a physical unit consisting of one or more CPU cores and the memory that's directly attached to them. So the CPUs can access the memory within that NUMA node faster than memory from other NUMA nodes. So in some cases, it can be advantageous to ensure that your CPUs are using the local memory. So looking at the NCI example command a bit more, in that example job, they have requested 384 CPUs for the whole job. They've set the NCPUs per task to 4, and they've defined a variable for the number of cores per NUMA node, and this is 12 on the Guardian normal queue. So if we expand out this equation, we can see that they're going to run 96 processes concurrently. So there was 1,000 lines in the input file. It's going to cycle through 96 at a time until it completes the end of the input list. And it's going to map 3 processes per resource. The resource is NUMA, and there are 4 CPUs per task. So given our understanding of the Guardian normal queues having 12 CPUs per NUMA node, 3 times 4 is 12, so that's a great setup for this particular queue. What if that wasn't the case for you? What if you wanted to use more CPU or memory than was available on a single NUMA node? For example, if you needed 24 CPUs per task, the equation would end up being 0.5. So we can't assign half a task to a resource. So this job is going to fail with a non-zero exit status and display an error message. So one way of doing that is, of course, to map by node, like in the simple example earlier. And if we do this with 24 CPUs, our memory is obtained from 2 whole NUMA nodes. If we needed 16 CPU per task, we would then be taking memory from 2 NUMA nodes, and some NUMA nodes will be providing memory to 2 different CPU tasks. Whether this is going to affect the performance of your job really depends on your workflow and the tools that you're using, So to assess potential memory latency, you should definitely do benchmarking to determine what the optimal number of CPUs and memory for your job is. It's important to note that if you do map by NUMA node, this only works if the remainder of n cores per NUMA node divided by n cores per task is 0, which it does for the NCI example. So let's consider an example where you've done benchmarking and determined that your task runs most efficiently with 8 CPU per task on the normal queue with only 1 task running per NUMA node. So it needs a little bit more memory. So 12 on 8 leaves a remainder of 4. So this binding is not possible. You would encounter a fatal error when you attempted to run this job. But you can achieve this same setup by assigning n cores per task the same value as n cores per NUMA node, i.e. 12. So then you could map 1 task per NUMA node. And then you would simply define an additional variable within the PBS script with your chosen value of 8 CPUs per task. And then you would ensure that your task script reads the 8 CPU variable, not the 12 CPU variable. So that way you're reserving 1 NUMA node per task and your actual task script is utilizing 8 CPU. So given that complexity, what's the advantage to mapping by NUMA node? I alluded to this earlier, it's memory performance, because the cores within that NUMA can access the memory faster than memory from other NUMA nodes. So your jobs can have improved performance if you're using only local memory to the CPU, particularly for memory-intensive applications. So again, perform benchmarking and understand if this is important for your workflow. For more advanced applications where you're interested in which sockets and CPUs within the node that your tasks are actually bound to, you can add this flag report bindings to the MPI run command, and this will tell you information about the sockets and the cores. So this is an example of a task running 6 cores in parallel and each 6 tasks in parallel and each task uses 1 CPU. Next, we'll consider CPU efficiency for parallel jobs. We talked about this in the benchmarking session 2 weeks ago, that we should always benchmark a single task to understand what the best resources are. And that's so important when you're looking at a parallel job, because the scale can potentially result in a lot more wastage of time and resources and service units if you haven't appropriately benchmarked. So we'll consider an example of how you can test your CPU efficiency for a parallel job after you've done benchmarking for a single task. Let's say you've chosen 12 CPU and 48 gigabytes of RAM for a 20-minute job for your task, and you have 1,000 of these tasks to run. If you wanted to run all of them in parallel, this equates to 250 normal nodes. Prior to submitting a 20-minute 250 node job, you should test 4 tasks in parallel. Now that's filling up 1 whole node. Does the CPU efficiency remain the same as benchmark for a single task? And then go on to test a handful of nodes, say 10. And then again, does the CPU efficiently remain fairly stable now that there's 40 tasks running at once? If so, you can go ahead and submit the remaining tasks. But of course, remember to remove these 14 tasks from your 1,000 input list. There's no point rerunning them. If not, what happened to the wall time and the CPU efficiency? If the decline in efficiency was very drastic and the wall time very much worse, you would definitely consider going back and re-optimizing from the start. If the decline was minimal, you can then extrapolate from this to estimate the wall time required for the job. And you could potentially, if you were unsure, run a larger scaling test, for example, the next 100 tasks in the input list, to obtain more accurate extrapolations. And then finally, keep records of all of this work for future reference, particularly if you frequently run the same job yourself or within your lab. You can keep good records and they can inform future jobs, saving you a lot of time. And always back up not only your job scripts, but also your resource recording to RDS so that they're not subject to scratch purge. A simple way of summarizing your benchmark runs and your job usage is with our Garda usage script, which I've mentioned in the previous session. It's simply a Perl script that summarizes logs within the same directory to a tab delimited text file, including the CPU efficiency, service units, and whatnot. So again, this sounds like a lot of extra work, but it can really save you a lot of time in KSU, and it's really critical on HPC that we are submitting efficient jobs, making good use of the resources, and also getting our results faster. By doing this little bit of work at the start, we end up at the final results much quicker. So looking at wall time management on NCI parallel jobs and how that affects CPU utilization, we'll discuss one potential disadvantage of NCI parallel jobs compared to PBS Job Arrays, and we'll look at some strategies of how we can minimise this with a few different methods. So in job arrays, each subjob of the array is a discrete task and it consumes its own chunk of resources. Those resources may or may not be on the same node as other subjobs of the array. They're completely separate. When each subjob completes, it returns its resources to the cluster and they become available for other jobs, so you're not accruing them against your account. In contrast, NCI parallel reserves the entire collection of resources for all parallel tasks in the job as one large chunk. So that means that if you have one really long running task and all the other tasks are quite short, the CPUs that the short running tasks were on will remain idle while the long running task completes, and you will still be charged for that. So your service units will go down and your job's overall CPU efficiency will be very, very low. So because of this, parallel jobs where there's a large distribution of wall time across tasks are important to actively manage and explore ways where you can stop this from happening. So here's 5 different strategies, and you can employ one or a combination of these to get a good result. The NCI parallel timeout parameter will cap the amount of wall time per task. And this is good for preventing unexpectedly long-running tasks from dragging out the wall time when all other tasks have completed. And then you can identify those failed tasks and resubmit them separately with longer wall times. You can request less resources than are required for all tasks to run in parallel. And this is recommended on the NCI Parallel User Guide, where it suggests 10% of tasks running in parallel. This may be appropriate for some workflows, not all, so don't think that you have to do 10%. You can use a loop to submit jobs only with modest numbers of parallel tasks, say less than 100, with varying wall time for each task based on the expectations that it will need. Please note that NCI discourages the use of loops for job submission on Guardi, which is why they created the NCI parallel utility, because they do overload the scheduler. So restrict this to small numbers of parallel tasks and always add a couple of seconds sleep between each job submission. Another method is to sort the tasks by expected order of wall time, longest to shortest, if known ahead of time, of course, and then request resources so that less than the total number of tasks are running in parallel. So use a combination of sorting and strategy 2. And finally, you can group subsets of parallel tasks by expected wall time. So for example, you can have a slow running job, a fast running job, and then something in the middle and submit 3 jobs instead of 1. So this figure demonstrates how this works in practice. So in the example here, we've got 5 tasks, and in figure A, you can see that the job was launched so that all tasks run in parallel. This obviously gives us the fastest possible wall time, but it does result in a lot of idle CPU, which is a shaded area here, so the least efficient way. In example B, the job has used strategy 2 and requested less resources than required for all tasks to run concurrently. So we definitely get a reduction in idle CPU, but unfortunately, because there's no task sorting, the wall time has increased. Figure C is the optimal method where strategy 2 and 4 have been used, so less resources than required to run all tasks in parallel and task sorting. So if you're not able to sort your tasks ahead of time, strategy B is definitely recommended, but strategy C, if possible, is the best one. So now we'll look at memory management within a parallel job. So we know we can control how many CPUs our tasks access with a user-defined bash variable. However, each of these parallel tasks has access to the total amount of memory. If you've requested a whole node, it can access up to the memory on that whole node. Or if you've requested less than 1 node, it can access all of the memory that you've provided in your -l mem directive. So in order to avoid memory contention between your tasks, you should, of course, benchmark your memory usage, have an understanding of what is the peak memory requirement per task, and request your resources in line with that. You can use nqstat_ANU, which provides live tracking of memory and CPU as a job is running, or if you're familiar with advanced profiling tools, please go ahead and use those. Another method, if possible, for your script or tool is to enforce memory limits per task. So this might be controlling Java mem, or if the tool has a flag for memory. So if you were using 4 CPU on the normal queue, you would cap each task to use at most 16 gigabytes of RAM. If memory contention does occur within your job, the first tasks to start are going to consume the available memory that they need, and then other concurrently running tasks that started later may run a lot slower or potentially even fail due to memory exhaustion. So depending on your tool and workload, this might result in individual task failures or potentially the whole PBS job failing. So please note that mapping by NUMA node doesn't prevent this. The CPUs can still access memory from other NUMA nodes. So now we'll move on to our example jobs section. We've got 2 examples to talk through. I'll talk through one with genomics, and Tom will give an example of calculating pi with Python. So I won't go over the background of this because I know everyone in the room is not a genomicist, but typically in this domain, there's a lot of potential for massively parallel jobs. We often work with tens or hundreds of samples at a time with lots of processing steps that can each often be broken up into smaller subtasks. So in this example, we have DNA sequences, which of course are completely independent. They're fragmented, and we just need to map them against a reference file. So for our example, 100 samples, we have 400 million DNA sequences per input file. Typically on Artemis, users would run this as a job array of 100, and it might take, say, 8 hours or potentially more to map all of these per sample. On Guardi, because of the extensive infrastructure that we have available and the very fast turnaround time on the queues, it's highly expedient to split the input into much smaller files. I recommend 10 million if you're working in this space. And then this will give each sample 40 inputs, and then we get a job that can be scaled up to 4,000 tasks in parallel. So let's assume prior benchmarking has been done. 6 normal CPU for 5 minutes is required on the normal node. This equates to 24,000 CPU or 500 nodes. So we can't run 500 nodes at once. The maximum you can run for a parallel job on Guardi is 432 normal nodes. We have a job calculator, which you can download here if you want to. It is just simply an Excel spreadsheet where you take your best resources from benchmarking of a single task, so 5 minutes, 6 CPUs, and the normal queue, pop them into these red cells here, and it will populate the rest of the fields. It will tell you how many nodes are required to run all tasks concurrently. We already worked out that that's 500. Then you go ahead and change this number here, number of nodes, to see what happens to your wall time and number of cores. And then you can take these informations into your PBS script directives. So reducing that to 250 nodes gives us 10 minutes wall time. That's still a large chunk of resources. So that might be a little bit tricky to schedule. So I would probably halve that again and do 125 nodes, giving 20 minutes wall time. And then I'd request, say, 30 to allow for a little bit of decline in efficiency. So I will say that in practice, physically splitting like this does require a handful of steps, but by running 4,000 tasks instead of 100, it is so much faster. The speed up is multiple times over, so you do save time in the long run. Compared to Artemis, there's really only 2 extra steps, and that is physically splitting. And of course, you could do these steps on Artemis as well if you chose to, and then merging the physically split data at the end. The other steps of checking your logs, creating your inputs file, setting up your task script to read the arguments, and setting up your PBS script are all the same between Artemis and Guardi. So now we'll look at an actual job array script from Artemis versus Guardi. So assume that we're going to run a 4,000 task job on Artemis. As I said earlier, you probably wouldn't, just because of the way that Artemis is set up as far as its queues, its queue time, and the number of nodes. But if you did, the inputs would look the same between Artemis and Guardi, a 4,000 line text file, And here's our Artemis Job Arrays script. I might try and make that a little bigger. So we have our directives and module loads at the top. Task inputs are read using the PBS array index to reference the relevant line of the inputs file, and the analysis is run. So one script to submit the tasks. We would have to submit this in 4 batches because we can only have 1,000 task job arrays on Artemis. Then on Guardi, we have a very similar setup. PBS directives and module loads, read the task inputs, and run the analysis. The analysis commands are identical. The input variables are read in slightly different command, but essentially the same. The PBS directives are slightly different, and that is described on our PBS Scripts page of this content. And then the main difference here is the NCI parallel command. So as mentioned earlier, you can simply copy paste this configuration from the simple example at the top of the content and adapt that with your CPUs, script and inputs, and this should run reliably for you every time. So looking at this, going on here. One of my banners suddenly popped up. Looking at this script side by side, you can see that there's very little difference. A critical difference to understand is that on Artemis Job Arrays, you're requesting the amount of CPUs per individual task. So each task wants 6 CPUs, 24 gigabytes of RAM, and 10 minutes of all time. On Guardi, we are requesting the resources for all of the tasks. So we're requesting 125 nodes for 30 minutes, and then each task is going to take 6 CPUs. So that's the end of that example, and I'll now hand over to Tom to take through his example 2 with calculating of pi.
Thanks, Kelly. Let me just get the sharing going. Hit the right screen. Is that the right screen? Yeah, it is, I think. Move things out of the way. Okay, can you all see that? Good. All right, thank you. Yeah, so just to follow on from Kelly's example, a lot of the stuff I'm going to mention here is pretty similar, but the example I'll use is a simple Python script that does a calculation of pi using a Monte Carlo method. Essentially, this script leverages a multi-processing library for internal concurrency within the script, but that script itself can then be submitted multiple times simultaneously to the queue, either using Artemis Job Arrays or the Guardi equivalent NCI parallel. And this is your kind of typical use case for a simulation style workflow, where you have a script that may have its own multi-processing internally and may have shared memory within it, or complicated things that are going on in a single node, but it can be submitted many, many times with varying parameters in an embarrassingly parallel way. Some of you who have done the Artemis training in years past may remember the script what is pi.py, and I'm just going to show that same script that we introduced there, but show how you can use it with Guardi NCI parallel. And the basic idea is it's a simple Monte Carlo simulation where you just pick random points within a square and you count the number of points that lie within a unit circle, and there's a very simple equation that gives you the value of pi. Of course, the larger number of times you throw darts or pick random points within that square, the closer you get to the true value of pi. The essential idea here is that this script is embarrassingly parallel, so each instance of it can be run independently, and just to get the final result, all you have to do is take the weighted average of all of the results for pi based upon the weight being the number of trials that go into the number of trials per run. So the script, I'll just put the script here very quickly. There's not much to say. So the actual calculation of pi is done by this pi run function. And then there is a function that will cycle through a given number of trials over a given number of processes. The important things to note here is within the script, it's using Python multiprocessing. It's using a thing called a pool. And we're mapping each of our estimated number of trials. We're mapping the function to calculate pi over each of our estimated number of trials to get our estimates of pi. And then at the end, we print out the results. So yeah, I've gone over what is going on in multiprocessing. So just as an example, if you run at the command line, if you want to use 2 CPUs with three trials of varying length, you would just run Python what is pi with first the number of CPUs and then varying numbers of trial lengths. And this would produce an output with 3 different estimates of pi. And then you can just convert those to a single estimate by taking the weighted average of those three smaller estimates. So now we'll go on to looking at running. So that's how the script runs itself on a single node or many instances of on a single node. Remember, multiprocessing can't see what's going on across nodes. So if you want to run this at scale, you have to use something like NCI parallel to run it multiple times. And so what we'll do is show how to do this, run multiple instances of the script, each with an independent pool of CPUs. First of all, just for the sake of comparison, I'll show you how you do this with an Artemis job array. And then I'll show you how we would very simply modify that Artemis job array to work with NCI parallel on Gardy. So first, what we do is we set up a set of job parameters. We just set up a file called job params that has a list of all of the parameters we want to pass to our different running instances of what is pi.py. I've kept this very short to keep the example clear, so we only have 4 separate runs. Of course, for a large HPC job, you might be running thousands of these parameter sets. But this is just for the purposes of clarity. I'm just restricting myself to 4 different runs of what is pi here. And so what we're going to do is run that script with 4 times using a job array on Artemis with these input parameters. And just to note, I've put largest run sizes here in the first 2 instances and the smaller run sizes in the next 2 instances. We know that these bigger number of trials are going to take longer to run. So I've sorted these as Callie described, and I'll show you the implications of that later on. So here is just a simple PBS script that uses job arrays on Artemis to run what is pi.py 4 times for each element of job params. Since this isn't a course on Artemis itself, I won't tell you the details of how all of that works, but essentially what happens is the script is run 4 times for each of the 4 sets of parameters appear in job parameters, and then it will produce a separate output and error.o.e file for each different run of what is pi.py. And just to note that on Artemis, each of these jobs uses a separate resource in the queue. It could be a separate node, but it basically, when one finishes, those resources are freed. They're not held onto. So each job can run for as long as it wants, and the resources are freed immediately afterwards. So to convert this to Gardy or to NCI parallel, it's relatively straightforward, as you know, it's very similar to what Callie showed earlier. What we would do is use NCI parallel to request 4 subjobs on a single node. Of course, if you were running this at scale, you would be running this over many we want 2 CPUs per subjob because that's what we've set in our set of parameters in our job params file. And we, as Callie described earlier, there's a simple equation that defines the number of subjobs that you're going to request when you run your MPI parallel command. When you run your MPI run command on Gardy. And so this is how you would convert the exact same script from Artemis to running on Gardy. The main differences are that we're now using MPI run instead of just a standard Python command, and that MPI run is going to loop over the elements of our parameters, but we've had to add the Python what is pi to the beginning of each line of our parameters, because what's happening with NCI parallel is that you're giving it the actual commands that you're running. And we're just running the commands directly here. We're not creating a separate shell script, mainly because our use case here is very simple. But generally, you'd probably create a separate shell script that you would run for a given set of parameters. And so just to say that the main differences here, and I think Callie sort of already covered quite a bit of this, but essentially in the PBS directives at the top, we're requesting all of the resources that we require at once. In the Artemis script, we're only requesting the resources that we require per node. So you just have to scale everything up to what you expect the total job to require. As I said, the Guardi script creates a new command file called input command, and that's just by prepending the Python 3, the command that runs the script to the list of commands, because that's what NCI Parallel requires. And we're using this map by parameter, and we're defining 4 simultaneous jobs, each using 2 CPUs. So here we're mapping by node. We don't care about shared memory and NUMA nodes here. We're just going to map by node. And yeah, using the equation that Callie showed earlier. And finally, the output files are named slightly differently with this implementation. So you can add a -O to NCI Parallel, and that will put the separate outputs from each of the jobs that it farms out into separate output files. And these will be called standard error.run number or ID and standard out.ID, and that's for the error and the standard output of each task. And we've set the general output from the job at the top in the PBS directives and to this NCI Parallel.O and NCI Parallel.E, and that gives you the general resource summary or info and failures. It lets you, as Callie said, it lets you see what, if any of your tasks have failed with errors and things like that in the general sense. So if we submit that job to the queue, we've requested 8 CPUs in total, and it runs for about 12 minutes, and it has used 3.19 service units. So just based upon the job that we gave it, this list of job params here, you can see the first 2 are very long running and the second 2 are very short running. So what's happened here is that the entire request of 8 CPUs is being used for the entire time that the longest job that will run is required. If you have a look at the figures in the example that Callie showed on. The link not working. No. Anyway, yeah. So if you have a look at these figures, in this case, we are in the first example where our longest job has run, but all of the other jobs have finished very much earlier, and we've wasted a whole lot of resources and ended up using 3 service units for this, or just over 3 for this task. So as Callie said, the best way to optimize this is to actually keep that. It's very important that you sort your list of inputs by expected, in decreasing order of expected runtime, which is what we've done. And then we just rewrite the script and separate the job into 2 tasks instead of 4, so only using 2 CPUs. We also have to change n CPUs equal to 4 instead of 8 in the PBS directives at the top of our script. And then our supplied calculation would do that for us. But here I've just explicitly shown how you would change the NPI run command to only use 2 CPUs instead of 4 CPUs. 2 CPUs with 2 tasks instead of 2 CPUs with 4 tasks for this job. And what happens then for the same input, we end up with only 4 requested CPUs, but we only use half the service units, and that is only at an increase of a very small increase. That's still only around 12 minutes or 3% increase in wall time for the job. So it's just to show you that, you know, it's easy on the surface to convert things from Artemis to Guardi. The scripts look pretty similar, and you don't have to make major changes. But it is worth thinking through the optimization of what you're doing before you do it, because Guardi has a slightly different way of submitting all of the jobs to the queue in one block rather than multiple jobs separately. And so yeah, that's the end of that example. Just quickly to go over, summarize everything. There are no job arrays on Guardi, we've seen that, but it is very simple to convert those to NCI Parallel. Definitely always benchmark your tasks. As I said, that you want to do benchmarking anyway to know what resources you're going to require, but also think about how your script is going to run on Guardi as opposed to Artemis, because you can save a lot of SU by doing that. Yeah, always take steps to maximize parallel job efficiency. Also, part of benchmarking, just make sure you map by, you think about whether you need to map by node or by NUMA node. NUMA node has much faster memory access for shared memory applications. When each task might need that on a single node, and it's worth just running some benchmarking with those two different use cases to see which one works for you. Yeah, what else do we have here? If you don't know how much you're going to need, always request less resources than you need to run all tasks concurrently. NCI recommends 10%, but you may even want to use slightly more or slightly less. It's what you always have to test these things out. And we have provided a calculator to adjust resource requests based upon benchmarking. There's a link there, or earlier on in this page. And yeah, that's right. Make sure you always check your logs when it's finished. So, in the case of the example I showed, I'm putting my output into the sort of global job output into NCI Parallel.o and NCI Parallel.e. You should always go through those to make sure all the tasks have finished successfully. They should have exit status 0. And also you want to, of course, check the log output of your individual commands. And it goes without saying, and I think we've mentioned this a few times, you should always redirect output from each of the individual tasks to separate files, because you don't know what order they're going to appear in. And if you don't redirect the output, they all just go to that global output file, and maybe in an order that is very difficult to disentangle when you've finished running your job. Yeah, and I think that's summarized everything. I'll stop and ask for questions. Is there anything in the chat or anything?
No, it's all clear in the chat. Thanks, Tom. Thanks, Kelly. Very good.
Cool. Well, I will stop sharing then. And yeah, this is the last of our little sessions, but all of this is going to be available online, including a recording of this session, and there's recordings of all the previous sessions we did. And as Kelly said, yeah, towards the end of the year or September, when Artemis goes down, I think we may think about doing these again, just for people who are at that point, we're all going to be forced to move over to NCI, so becomes a bit more urgent.
Good stuff, Tom. Thanks a lot. All right. Thanks, Kelly.
Thank you. Thanks everyone for coming along.
See you soon.
See you. Bye.